Good morning, students. Today we are going to see this Ionic Equilibrium, unit number 8, and this is video number 2. The main objectives of this particular video class is to understand and calculate pH and pOH definitions and values, to learn the common ion effect, and third, to understand the buffer solutions and buffer effect. So these three headings we are going to see in this particular video class. The first one, pH scale. We usually deal with acids or base solutions in the concentration range from 10 power minus 1 to 10 power minus 7 m. To express these concentrations, Sorensen introduced a logarithmic scale known as pH scale. This term pH is derived from French word. What does it mean? pH. Puissance dehydrogeny. What is the meaning of that? That is the power of hydrogen. pH means power of hydrogen, but actual the meaning is from French word puissance dehydrogeny. The pH of a solution is defined as the negative logarithm of base 10 of the molar concentration of the hydronium ions present in the solution. The equation can be given like this: pH is equal to minus log base 10 H3O plus ion concentration, hydronium ion. This is equation number 8.5. Please remember this. Often we will repeat the same equation. The concentration of the hydronium H3O plus in a solution known pH can be calculated using the following expressions. So how to calculate? You might have studied log form and without log form. You have studied in mathematics during 9th or 10th standard. The same here, we have to apply the H3O plus is equal to 10 power minus pH. The same expression without log we have to write like this: H3O plus gives 10 power minus pH, or otherwise H3O plus ion concentration is equal to antilog of minus pH. Antilog of minus pH. Similarly, the hydroxyl ion concentration, that is pOH, can also be defined as follows. So pOH is equal to minus log to the base 10 hydroxyl ion concentration, OH minus ion concentration. As we discussed earlier, in neutral solutions, the concentrations of hydronium ion as well as hydroxyl ion is equal to 1 into 10 power minus 7 m, usually at 25 degrees Celsius. The pH of a neutral solution can be calculated by substituting this hydrogen ion concentration in the expression 8.5 equation, the first equation. That is pH is equal to minus log to the base 10 hydronium ion H3O plus ion concentration. So if you substitute the value of H3O plus ion concentration as 10 power minus 7, we will be getting minus log to the base 10 power minus 7. Using the power rule, in logarithm we have a power rule that minus 7 will come before as a coefficient. So minus 7 into minus 1 log 10 base 10. So minus 7 into minus 1 becomes 7. Logarithm of 10 base 10 becomes 1, and therefore 7 into 1 is equal to 7. We will be getting as the answer for this particular equation. Similarly, we can also calculate pOH of a neutral solution using the same expression 8.7, which is also equal to 7. The negative sign in the expression indicates we have minus log concentration only, no? That negative sign expression indicates when the concentration of hydrogen ion increases, the pH value decreases. Both are inversely proportional. Hydrogen ion concentration is inversely proportional to pH value. If one increases, the other one decreases. For example, if the H3O plus increases from 10 power minus 7 to 10 power minus 5 m molality, the pH value of the solution decreases from 7 to 5. The value becomes 7 to 5, decreases. When the concentration increases from 10 power minus 7 to 10 power minus 5, the pH value decreases. We know that in acidic solution, hydronium ion concentration is greater than hydroxyl ion concentration. That is, H3O plus is greater than 10 power minus 7. Similarly, in basic solution, H3O plus is less than 10 power minus 7. So, we can conclude that acidic solution should have pH value less than 10 and the basic solution should have the pH value greater than 7. Another important question in this particular lesson is a relation between pH and pOH. So, the derivation often comes for a 3-mark question. Please go through and listen. The relation between pH and pOH can be established using their following definitions. The first definition, which I have already seen, pH is equal to minus log concentration of hydronium ion to the base 10, and pOH is equal to minus log concentration of hydroxyl ion to the base 10. So, adding these two equations, before that we have certain substances with the pH value. See that inside our bile stomach, the acid, its concentration is pH value is 1. In battery, acid is 0, and orange juice, the pH value is 3. Vinegar, acetic acid, the pH value is 2. Similarly, in this diagram they have given, and down if you see, even for sea water the pH value is 8. Therefore, it is basic in nature. Since it is greater than 7, sea water on the right hand side, if you see, there is 7, 8, and urine, its pH value is 6. Therefore, it is acid. Uric acid will be present. Okay. So, similarly, all the values are given. Please go through this diagram. And then adding this pH and pOH, minus log to the base 10 concentration of hydronium ion minus log to the base 10 minus hydroxyl ion concentration. So, if you take minus common outside the bracket, we will be having plus in between. So, log hydronium ion concentration plus log hydroxyl ion concentration. So, pH plus pOH is equal to, using the product rule, this hydronium ion concentration and hydroxyl ion should be multiplied. This is what you call product rule in logarithm. That is, log A plus log B is equal to log AB. This is the formula. So, applying this formula, we will be getting minus log hydronium ion concentration into hydroxyl ion concentration to the base 10. We know that hydronium ion concentration into hydroxyl ion concentration is equal to Kw. That is ionic product of water. It is called ionic product. So, pH plus pOH gives you minus log Kw to the base 10. pH plus pOH is equal to pKw, that is minus log 10 becomes P. So, minus log 10 becomes P, therefore, Kw is Kw as usual. The next, at 25 degrees Celsius, the ionic product of water is equal to 1 into 10 power minus 14. So, substituting this value in this above equation, we get pKw is equal to minus log 10 power minus 14 to the base 10. So, using again the power rule, the minus 14 will become multiplication at the before coefficient, and the minus into minus becomes plus. Log 10 to the base 10 becomes 1, therefore you will be getting 14. So 8.7 implies that at 25 degrees Celsius, pH plus POH together, that is the concentration of hydrogen ion, concentration of hydroxyl ion, both together is equal to 14. One example is given. Calculate pH value of 0.001 m HCl solution. This can also be written as 1 by 1000 m HCl. Okay, the concentration. Equation is HCl gives H3O plus Cl minus in the presence of water molecule. It is an equilibrium reaction. Hydronium ion from the auto ionization of H2O 10 power minus 7 molality is negligible when compared to the H3O from 10 power minus 3 m molality of HCl. So hence H3O plus is equal to, it's given in the sum itself, 0.01 mole per dm cube. So if substitute this value in this equation, pH is equal to minus log concentration of hydronium ion, we will be getting 10 power minus 3. So minus 3 will become multiplication of minus into minus 3, log 10 base 10 becomes 1. Therefore the final answer is 3. So similarly we can calculate so many other values also. Let us see. Then calculate pH of 10 power minus 7 m HCl. For this one example is given. It is not good for me to go through by explanation. Let me explain in a class, regular class. Now let's go for the next, ionization of weak acids. Let us consider the weak acid as HA. Okay, see the equation, HA plus water gives H3O plus A minus. So this is what you call ionization of weak acid. The weak acid is HA. Applying the law of chemical equilibrium, the equilibrium constant Kc is given as, Kc is equal to, that is concentration of the product divided by concentrations of the reactants. So if you multiply all those things, say H3O plus concentration into A minus concentration divided by HA into water concentration. So this is what Kc, that is equilibrium constant. In this square bracket usually means the concentration. In dilute solutions, water is present in large excess, hence the concentration may be taken as a constant. So H2O concentration can be taken as constant, which is equal to K. So the equation becomes Kc is equal to hydrogen ion concentration into A minus ion concentration divided by HA into K. So 2 K's we are having, 1 Kc is equal to, on the right hand side we have a K. So both are constant, so we can mix together. See the next equation. So the product of the two constants Kc and K gives another constant, let it can be Ka. So the remaining becomes HA, H and A. So the constant Ka is called dissociation constant of the acid. Like other constants, Ka also varies only with temperature. Similarly, we can apply this same rule for the base also. So base equation Kb is equal to B plus into OH minus ion concentration divided by BOH. So this is the way in which the ionization of water can be calculated. And the next, Ostearthritis dilution law, very important law, often comes in the examination, so please remember. Let's go through this one. Ostearthritis dilution law relates the dissociation constant of weak acid, that is Ka, with its degree of dissociation, which is alpha, mentioned as degree of dissociation symbol is alpha, and the concentration, which is C. So the degree of dissociation alpha is the, what do you mean by degree of dissociation? It is the fraction of the total number of moles of a substance that dissociates at equilibrium. Please remember this. What do you mean by degree of dissociation? There is a fraction of the total number of moles of a substance that dissociates at equilibrium. For example, there are 100 moles. Out of 100 moles, only 10 moles are dissociating, means the fraction is 10 by 100. That is 1 by 10 it becomes. This is what you call degree of dissociation. The total number of moles will be down and the number of moles dissociated will be on the numerator, so you will divide. So this gives you the value. So alpha is equal to number of moles dissociated divided by total number of moles. Please remember, this is the formula for dissociation. We shall derive an expression for Osteoarthritis law considering a weak acid. Acetic acid is the example. Acetic acid can be dissociated as follows. CH3COOH gives, there is an equilibrium request, H plus and CH3COO minus. The dissociation constant of acid is given, Ka is equal to, for the same equation, the concentration of the products divided by concentration of the reactant. So H plus ion concentration into CH3 acetate ion concentration divided by acetic acid concentration. Now let us see one tabular column here. The initial number of moles in the above equation, if we take, acetic acid is 1 when the reaction does not take place at the initial state. There is no H plus, there is no CH3COO minus. Therefore, both becomes dash dash. Now, after some dissociation takes place. So, how many dissociated? There is alpha dissociated. So, what is remaining? 1 minus alpha is remaining. So, at equilibrium, so 1 minus alpha is remaining, CH3 acetic acid, and H plus ion is alpha and acetate ion is also alpha. So, what will be the concentration? Equilibrium concentration. So, the number of moles into C, that is concentration, you have to multiply. Therefore, the first one, acetic acid, becomes 1 minus alpha C, hydrogen ion concentration becomes alpha C, and acetate also becomes alpha C. Substituting these equilibrium concentration in equation 8.13, we get Ka is equal to alpha C into alpha C divided by 1 minus alpha C. So, alpha square C by 1 minus alpha. The C and C will get cancelled. One numerator C and denominator C will get cancelled. So, this is what we call Osteoarthritis dilution law equation. Alpha square C divided by 1 minus alpha. So, we know that weak acid means dissociation only to a very small extent. So, dissociation is very negligible, that is alpha is so small. So, if we take into consideration the denominator 1 minus alpha, alpha value is nothing, therefore, we can take it as 1. So, numerator becomes 1, therefore, the formula becomes Ka is equal to alpha square C. So, from this we have to find out the dissociation constant. So, take alpha square on left hand side, you get Ka by C. So, what is alpha? Take the square root of Ka by C. So, this is another important equation of the Osteoarthritis dilution law. So, let us consider an acid Ka with value 4 into 10 power minus 4 and calculate the degree of dissociation of that acid in two different concentrations. Two concentrations were given, 1 into 10 power minus 2m and 1 into 10 power minus 4m using the above expression. Okay. Now, for the first one, alpha is equal to, substitute the value. So, we are getting 4 into 10 power minus 4 divided by 10 power minus 2. So, when you cancel, you get 10 power minus 4 and 10 power minus 2 becomes only 10 power minus 2. So, 4 into 10 power minus 2, square root means 2 and 10 power minus 1. When you take square root of 10 power minus 2, it becomes 10 power minus 1. So, 10 power minus 1 is nothing but 1 by 10. So, 1 by 10 into 2 is equal to 0.2. Similarly, for 10 power minus 4, we get 2. So, when the dilution increases by 100 times, the concentration decreases from 1 into 10 power minus 2 to 1 into 10 power minus 4. The dissociation increases by 10 times. So, this usually comes in an objective type question. Please remember, when the dilution increases by 100 times, the dissociation increases by 10 times. So this is the proportion. Remember, this is an objective type question. So we can conclude that when dilution increases, the degree of dissociation of weak acid electrolyte also increases. This statement is known as Ostearthritis dilution law. So both are increasing. Dilution increases, the degree of dissociation of weak electrolyte also increases. This is the statement. So the concentration of H plus and H3O plus can be calculated using Ka values as down. So hydrogen ion concentration is equal to alpha into C. So equilibrium molar concentration of H plus is equal to alpha into C. So substituting these values in this equation number 8.15, we are getting square root of Ka by C into C. So that numerator square root C and another denominator C will get cancelled. So finally we will get hydrogen ion concentration is equal to square root of KaC. Similarly for base also, hydroxyl ion concentration is equal to square root of KBC. So these two equations, again it may come for some sums also. Hydrogen ion concentration and hydroxyl ion concentration. Square root of Ka into C, square root of Kb into C. These two equations 8.17 and 8.18, both are very important equations of the dilution law. The next subheading is common ion effect. So what do you mean by common ion effect? When a salt of the weak acid is added to acid itself, the dissociation of the weak acid is suppressed further. For example, the addition of sodium acetate to acetic acid solution leads to the depression in the dissociation of the acetic acid, which is already weakly dissociated. In this example, acetic acid and sodium acetate have the common ion acetate ion. So let us analyze what happens. See the first equation. Acetic acid gives H plus ion and CH3COO acetate ion, and sodium acetate gives sodium ion plus acetate ion. In this both the cases we have acetate ion as common ion. So this is what you call common ion effect. So overall concentration of the acetate ion is increased. Therefore the dissociation of the salt is depressed. So this is the common ion effect in this particular equation. If you completely read, you can understand. Then buffer solution. What do you mean by buffer? See, our blood maintains a constant pH, which is also considered as a buffer solution, irrespective of number of cellular acid-base reactions. It is possible to maintain constant hydronium ion concentration. Such reactions, it is possible due to buffer action. So buffer is a solution which consists of mixture of weak acid and its conjugate base. Once again, buffer is a solution which consists of mixture of weak acid and its conjugate base. A weak base and its conjugate acid. So either this one or that one. This buffer solution resists drastic changes in the pH. So when the buffer is present, it does not allow a very large change in the pH value. It suppresses the change in the pH value. So addition of small quantities of acids or bases, this ability is called buffer action. The buffer containing carbonic acid and its conjugate base HCOO3 minus present in our blood. Therefore, two types of buffer solutions are there. One is known as acid buffer, the other one is known as basic buffer. So what is an acid buffer? So this is another important 3-mark question. What are the types of buffer solution? Acidic buffer and basic buffer. A solution containing weak acid and its salt is known as acidic buffer. Example, acetic acid and sodium acetate. And the next one, basic buffer solution, a solution containing a weak base and its salt. Example, ammonium hydroxide and ammonium chloride. So please remember, this is another 3-mark question. Types of buffer solutions, acidic and basic buffer. Very simple examples are also there. The next, buffer action. To resist the changes in the pH, please underline this word, resisting the changes in the pH. This is the role of buffer action. Okay. Addition of an acid or a base, the buffer solution should contain both acidic as well as basic components as to neutralize the effect of added acid or base. So whatever you add, if you add acid or base, it will neutralize and it maintain the pH value. The components should not consume each other. This is one condition. So let us explain one buffer action. Acetic acid and sodium acetate, both the equations which I have just now seen. Acetic acid dissociates into acetate and hydronium ion. Sodium acetate dissociates into acetate and sodium ion. If an acid is added to this mixture, acid means we have H plus ions. When acid is added, it combines with acetate ion and forms acetic acid. So there is no change. If base is added, the base means OH minus is added to the hydronium ion H3O, it becomes neutralized. It becomes water, H2O. So it is neutralized. So there is no change in the basic. Therefore, the final equation becomes CH3COOH in presence of water gives acetate plus hydronium ion. So consolidation equation is given down. OH minus ion plus CH3COOH gives CH3COO minus aqueous plus water. So these neutralization reactions are identical to those reactions that we have already discussed in the common ion effect also. It is similar to the common ion effect. The next one, another example here, one dissociation constant. The values are given. This we have to do it in the blackboard. And let me do it in our regular class. So this pH value, finally we are getting it as pH is equal to 4.75. Buffer capacity and buffer index. So the buffer ability of a solution can be measured in terms of buffer capacity. Van Slyke introduced a quantity called buffer index, that is beta. Remember, once it was asked in an objective type question, beta is equal to dB by dpH. So this quantity measure of buffer capacity, it is defined as the number of gram equivalents of acid or base added to 1 liter of the buffer solution. The next final one is Henderson and Hasselbalch equation, a very important 5-mark question. We have already learned that concentration of hydronium ion in each acidic buffer solution depends on the ratio of the concentration of weak acid and concentration of its conjugate base. See the equation, hydronium ion concentration is equal to Ka into concentration of acid divided by concentration of base. This is equation number 8.20. Please remember, hydronium ion concentration is equal to Ka into acid concentration divided by base concentration. Here the weak acid is dissociated only to a small extent. Moreover, due to the common ion effect, the dissociation is further suppressed and hence the equilibrium concentration of the acid is nearly equal to the initial concentration. Similarly, the concentration of the conjugate base is nearly equal to the initial concentration of the added salt. So the equation once again it becomes hydronium ion concentration is equal to Ka into the concentration of acid divided by concentration of the salt. Taking log on both sides. So log hydronium ion concentration is equal to log K plus log acid by salt, because we are using the product rule. Therefore, the multiplication becomes addition here. Log K plus log acid by salt concentration. So, introducing minus sign on both sides. So, we are getting minus log hydronium ion concentration minus log K minus log acid by salt. Here, we know that when minus log is there, we can change into P. Therefore, pH is equal to minus log hydronium ion concentration, pKa is equal to minus log Ka. Therefore, the equation becomes pH is equal to pK minus log acid by salt concentration. So, changing the numerator and denominator, we can change the sign also. So, minus becomes plus. Therefore, the equation becomes pH is equal to pKa plus log concentration of salt by acid. Above we are having acid by salt, here we are having salt by acid. Therefore, we have changed the sign from minus to plus. So, final equation for POH, similarly for basic buffer, POH is equal to pKb plus log salt by base. Instead of acid, we have salt. So, these two equations are known as very important Anderson-Hasselbalch equation. One example is also given. Simply we have to substitute the concentration of the salt and concentration of the acid in this equation. So, pH is equal to pKa plus log salt by acid. What is the sum? Find the pH of the buffer solution containing 0.2 mole per liter sodium acetate and 0.18 mole per liter acetic acid. So, two concentrations are given. What is that? Sodium acetate and another one is acetic acid. So, acid concentration is given and salt concentration is also given. Substitute in this formula, we will be getting the answer here as 4.74 plus log 0.20 divided by 0.18. So, if you finally substitute, you will be getting the value as 4.79. Students, please find out the answer for this sum. Do it in your notebook. In the regular class, I will try to do once again. So, the final assignment for this particular video class, I have given you 4 questions. The first one, write the relation between pH and POH, and the second one, explain Ostearthritis dilution law. Third one, what is common ion effect, and the fourth one, write notes on buffer solution. So, that's all. Thank you very much. Wish you all the best.